what it is, because it might be modified by the turbulence also. But so this displacement speed here, we can just get it from the equation, because if you look at this equation, you see that an isosurface here, it would move in time by three effects. It would move because of the convection. It would move because of the diffusion here, or the heat conduction, and it would move because of the reaction source term. But if you sit on the front, then these terms here, of course, just describe you're sitting on the front, and so the front moves by these two effects. And so you can actually, this expression just tells you how a reactive scalar front moves. And so this is this propagation velocity. The normal vector here, of course, on this front is defined here again with the gradient of the field. And then we can just call, here in this thing, we can just call, because t here is now the t at t naught, or is t naught, so we can just call this a g here again instead of t naught, and then we get a g equation where this here now is the propagation speed. Now this propagation speed has this diffusion term. The diffusion term here can be split up into a normal diffusion, a diffusion normal to the front, plus a curvature term, or a term that describes the curvature of the front. And then I can rearrange these and say I have three terms now. One is a curvature term, this one here, or comes from this. And the second one is the reaction term, this one, would be this. And then the third one is the normal diffusion, which is this. And now we want to say, well, if you think about what laminar flame propagation is just the combination of reaction and normal diffusion. Okay? So we say this reaction and normal diffusion, these both together, they should be something like a laminar burning velocity. Maybe a little disturbed, but it should be something like the laminar burning velocity. And so we just call this here the laminar burning velocity and assume it's basically the same. And then we have this curvature term. Okay? So now, so there's a difference. We said earlier in the corrugated flame regime, we have a flame, and the curvature radius, let's say, of this flame is much, much larger than the flame itself. And then the flame just moves by, laminar flame propagation. But now we say, okay, in the thin reaction zones regime, this is how the flame front looks like. It's very corrugated. And then this is the thickness of the flame. This would be the flame thickness. And then you see now the curvature radius for this and the flame thickness, they're on the same order. And you see you get diffusive effects which make this flame propagate. And that's what this term here, is. That this term here just says the diffusive effects now, which also make, because the curvature is so strong, which also make the flame propagate. And so now we have this equation. We can analyze this equation we set the interaction. So what's the difference here? The difference here is the interaction of the flame front with the Kolmogorov scale eddies. Okay? So we want to analyze this equation on the Kolmogorov scale, and so we non-dimensionalize everything. The time with the Kolmogorov time, the length scale here with the Kolmogorov length, and so on. Everything is the curvature here, the curvature with the Kolmogorov scale, and so on. Everything with the Kolmogorov scales. And if I plug this in the equation, then this is what I get. And this is interesting now because it's non-dimensionalized on the relevant scale. You see that all the non-dimensional terms, they should be order 1. Okay? Because that's because we choose the right non-dimensionalization. And then you see the two factors here, dimensional factor, or they're also non-dimensional, but these are now the non-dimensional groups. And the 1 here is d divided by nu. We often say Schmidt number equal to 1. That should be very close to 1. So let's forget about this term here. But then we have SL by U eta. And that's, of course, we don't know what it is. And it turns out that SL divided by U eta, that's on the order of Karlowitz to the minus 1/2. And so that's interesting because the Karlowitz number is exactly what distinguishes these different regimes. And so you can see if the Karlowitz number gets very, very small, okay, let's see if we write this here somewhere. No, this here just shows why it's Karlowitz to the minus 1/2. But if the Karlowitz number gets very, very small, then this here gets very, very large, and that means that this whole term gets very large, whereas this here stays order 1. So when the Karlowitz number is very small in the corrugated flame regime, it's only this term that's important. This term here goes away. Okay, that's what we know already. And then if the Karlowitz number gets very, very large, this is in the thin reaction zones regime, very large. This means then this term here, this factor gets very small, this term is very small, and this term stays order 1. So in the thin reaction zones regime, it's this term that's the most important one. Okay? So if we just say, okay, in the corrugated filament regime, we had an equation that just looked like this. But even in the corrugated filament regime, we can just add this term because it's very small anyways compared to the rest. Okay, and in the thin reaction zones regime, well, we just keep this term here also because this is also very small compared to this term. So we can look at this then as an equation that describes the leading orders in both of these regimes. So this is an equation that's valid in both of these regimes. Good, so that's what we want to use then. That's the equation that we use as a basis now. And well, this here just shows some statistics that you get in a real flame. If you look at the G here as the distance from the flame. So this here is a swirl burner, a weak swirl burner. This is the burner of Robert Cheng at Berkeley. The idea here is to have a burner with a very weak swirl so that you don't get a recirculation region, but you get a diverging flow, and then you stabilize the flame with a diverging flow, but you don't get a recirculation, so the residence time is fairly low, and you don't get much NOx because NOx formation is slow, and the higher the residence time, the more NOx you get. So this is basically developed for low NOx, and so experiments were here done in Aachen, actually using this burner, and then you have here the probability of finding the flame at a certain position here downstream of the burner, and you see the flame moves up and down. Interesting here is that it is pretty independent here of this V prime over SL. Now the location with respect to the flame. So if you take this now, this is the flame, the PDF of the flame position. That was this PDF here times the x coordinate itself integrated over this. That again gives you the mean flame position. So XF here, that would be the mean flame position. And then also you can define a variance here or a departure from the mean flame position like this. And we can define if we say G is a distance function, then G prime, that would be the fluctuating distance from the mean flame front, measuring, if this is a turbulent flame, what's the departure of the flame position from the mean? And then we can derive equations. Starting with this equation I showed you earlier, we can derive equations here for the mean G and level set, and for the variance of the level set. And so the mean here, that gives you the mean flame position, and this variance, it tells you what the departure of the flame from that mean flame position is. That's important. You can imagine because if you just look at the mean, you could say, the one side is burnt and the other side is unburned, and that would give you a density field, but the density field, of course, that would be very steep. I mean, that would have a discontinuity. But if in a real flame, flame looks like this, and if I do many, many measurements, then sometimes you get the burnt, sometimes you get the unburnt, and so you get a very gradual transition here from unburnt to burnt, and that's what this variance here of the level set means. And so we call this sometimes also the flame brush thickness. Okay, the thicker the flame brush is, the larger this variance will be, and the more gradual will be the mean temperature profile through the flame. Okay, so this variance equation here, so that's important, to get the temperature distribution, let's say, or the species distribution, density distribution. And it's an interesting thing to look at, because you have these, let's look at the terms here again. So it's an unsteady term, convection term. You see this here is a sort of a scalar flux term. So this is a turbulent transport term. You see this here looks very much like a production term. So you see the velocity field here, the fluctuating velocity, the turbulent eddies, they create new flame surface. That makes sense. And then here, this is a laminar term, so that might be neglected. But I have two of these sink terms here, this omega and the chi sink terms, and these two take flame surface away. Okay, they make the flame surface smaller, and so it's interesting to look at the effects. So where do these come from? You see this omega here. It again involves this SL, and that's what we said earlier. If you have a flame like this, take this one here. You see, you have a turbulent eddy that creates flame surface. But then when this flame here, when it burns, it propagates normal to itself, and something like this here will just burn out, and so the flame surface will go away. This is what this is here, because see, it has this SL term, and this is why we call this the kinematic restoration. So it restores the flame front to basically a flat flame by its own kinematics. And then the other term here, the chi, you see this has this looks very much like a scalar dissipation term. It's the gradient of a fluctuation squared times d, so that is a dissipation term. And that's exactly what this is. You have what the turbulence does, the small-scale turbulence now does in the thin reaction zones regime, is it creates a flame surface or creates this wrinkling, but it creates a wrinkling on the scale of the flame thickness, and just by diffusion then, just by the diffusion process, a corner like this will be taken out, and you will get a flatter flame just by a diffusion process. And so that's the scalar dissipation. And so these two terms here really, you can say this here is the governing dissipation here of this variance in the corrugated flame regime. And this one is the governing term in the thin reaction zones regime. So both together are modeled like this, where again, this is important in one regime and this is important in the other regime. And then, we have these different equations here. Here we introduced the turbulent burning velocity. And turbulent burning velocity, in the last lecture, we had a model for that also. And so then these equations here, they would be closed and could be solved in the RANS context. In the LES context, things look a little differently, but not very much. Again, this was the ST formula here we had earlier, and that can be just used now. Okay, so once we have the solution for the G field and for the G variance field, the G field tells us, the G field basically tells us where the mean flame position is, and the variance basically tells us what is the distribution of the flame around this mean position. And so if we make an assumption, so there's a presumed PDF here, if we presume the PDF of this G to be a Gaussian function, that depends now on the mean and the variance. Then we can use that to compute the mean temperature, and that then will give us, you know, a smooth transition from unburnt to burnt because of the turbulent fluctuations. And you see here, if this variance, in the laminar case, this variance would go to 0, this would be basically a delta function, and then also the temperature would have a jump here from unburnt to burnt. Okay? So that's how you compute the temperature, and then from the temperature you can compute the density, and the density is what you need in the momentum equation, and then the system is solved, is closed. So this here is, these are just examples. This here is just a Bunsen flame, and you see this is the simulation here, this is the experiment, and you could say, well, some things look similar and some things don't. This is the experiment here also. This OH here from the experiment. This here is a simulation that we have done some time back. This is an LES simulation of a turbulent Bunsen flame also. You see here in gray the flame surface. On the upper side here you see the temperature. There's a pilot flame here also, which is why the temperature is high. So you have pilot here, and then through this nozzle here you have a unburned methane air mixture coming in, and then this flame burns into this mixture. On the lower side here you see the temperature, you see the velocity, and you see how around the flame you get this acceleration that we also discussed earlier a few times. And then around this actually is air, and that's why, you know, downstream the hot combustion products, they mix with air, and this is why the temperature goes down here in the downstream region. So this is the comparison. Was there a question? No. This is the comparison with experiments where you see this close to the nozzle, you see the temperature on the left side and the velocity on the right, where the blue lines and symbols are the non-reactive, and the red is the reactive. Velocity field, and so you see it's you know, it's captured all right. And then if you look further downstream, again there's the non-reactive and the reactive, and again you see it's captured fairly well. Temperature is some difference here, but that's most likely because of the pilot. The pilot flame has a lot of heat losses to the burner, and it's very hard to estimate this. How much of heat losses you have. I mean, especially the maximum temperature here should actually be the same if you have the heat losses correctly described. This is interesting now. You see the velocity here. It changes from non-reactive to reactive, again because of the heat release and the induced velocity acceleration. But what's more interesting here is to compare the kinetic energy, the turbulent kinetic energy, and you see the non-reactive case has a lot more turbulent kinetic energy than the reactive case. Why is this? Why is this? No? Right, so that's one effect, two effects really. The one effect is that you change the Reynolds number. Okay, the Reynolds number becomes much smaller because the temperature now is higher. Viscosity increases, Reynolds number gets smaller, and because of that you have less kinetic energy. But people have, the smart experimentalists, so what people have done is they run a non-reactive jet, and then they run a reactive jet at a much higher Reynolds number, so that with the heat release, the local Reynolds number should be the same again. And then also in that case, you see much lower turbulent kinetic energy in the reactive case. The second one is that you see just around the front, you have heat release, you have a dilatation. So you have a heat release in one front, and then you push the gases left and right. Okay, so basically the gases left and right of the flame, they push on the you know, there's a pressure that pushes on the flame front and makes it more smooth. And so because of this, you just damp out also the this induced heat velocity acceleration it damps out the turbulence also. So that's another thing. And you see that the simulation picks that up also to some degree. This is not in your handouts, but I promised this yesterday, so I put this in. Is the regime diagram for LES. LES is interesting because think back at the regime diagram we had yesterday. What was it? It was U prime over SL as function of LT divided by LF. Now, what is for LES? What is the turbulent length scale? Well, an interesting turbulent length scale for LES is the subfilter turbulent length scale. And the subfilter turbulent length scale is delta, basically. That's our filter width. And the issue is that now you can change your filter width, and it seems like by just changing the filter, you go to a different combustion regime. Because, you know, I make the filter smaller, and I might move from one regime into the other. And so that doesn't make sense because the combustion regime is just physics, has nothing to do with the numerics. And so this regime diagram, it distinguishes between the numerics and the physics. You see, on this axis here, we set the Karlovitz number. That's the most important parameter. So on this axis here, we just have the Karlovitz number. So if you change the physics, you walk along this line. You leave this here untouched. You just walk along this line. If you just change the numerics, meaning you change your filter size in LES, you just walk along this line. You don't go this way. And then you see here from, if I, for example, in the thin reaction zones regime, then I can change the filter size, but I cannot move from thin reaction zones into corrugated fluid regime, or from thin reaction zone to broken reaction zone regime by changing. I cannot change the physics by changing the filter size. That makes a lot of sense. What is interesting, though, you can cross this line here. What is this line? Oh, let's say first this line here. Okay. So if I'm here and I make my filters smaller, at some point I get to a regime where my filter is smaller than the Kolmogorov scale, which means now I resolve all the turbulence. It's called resolved turbulence, but it's still larger. The filter is still larger here than the inner layer. So I don't resolve the flame. I resolve the turbulence, but not the flame. So this is resolved turbulence. If I go below this line here, then my filter size or my mesh is smaller than the inner layer of the flame thickness. So here I resolve both the turbulence and the flame. So this is the real DNS, just in this region here. And then this line here is interesting because we said in the thin reaction zones regime, the flame, it's not infinitely thin because the turbulence mixes in the preheat region. So the turbulence it broadens the preheat region. So you can estimate the thickness by using scaling arguments, the thickness of the preheat region of the flame in that regime, the turbulently broadened flame that has thickness, what's called here LM. Turns out that LM goes, or LM over delta goes with the Damköhler number. That is a place where the Damköhler number is important. And so this means if I'm here, then the flame, or if I'm here, then the flame is still so thin, that all this broadening here, it's on the subfilter scale. My filter is larger than even the broadened flame. Okay, in this regime, but in this regime. But I go in this regime, then some of the flame is resolved. Then my filter becomes smaller than the thickened flame, and then now I resolve some of the thickening of the flame. Okay, so this line is not so important. Okay, so that's more interesting. And now what we did here. There's the two more interesting things here. We took from this simulation at each point along the flame front, we evaluated these parameters, Karlovitz number and this, and then we plot each point in this diagram. And one thing you see, it's in this region is very narrow. That is because the mesh size is basically the same everywhere, or is little variation of the mesh size in this direction. And then, but there's a broad distribution in this direction. So this is something we always should keep in mind. When you look at an experimental paper, I showed you a DNS paper earlier, where we said you can evaluate the nominal Karlovitz number or Dampköhler or U prime over SL or whatever, the nominal values. And very often you see that people use a regime diagram and put a point here and say, this is where my flame is. Okay? But this is not where the flame is, because this is the nominal value for the flame. But locally, of course, you have fluctuations, turbulent fluctuations. You have variations in U prime. You have variations in all these quantities, and so you get a very broad distribution. Even if this is my nominal value, I get much smaller Karlovitz numbers and also much larger Karlovitz numbers. Okay, and the other one actually, the F2 flame, it even goes here locally in this broken reaction zones regime. So that's one thing to be mindful of. So when I said earlier, well, we have a model here that's valid in the corrugated flame regime. If this thing is nominally let's say it is nominally in the corrugated flame regime, then you would always see that you get a lot of stuff also in this regime and maybe over here. And if it's nominally in the thin reaction zones regime, you might get some locally, some regions that are here and some that are here. Okay, that's always something to keep in mind. We shouldn't always think only of the mean quantities. We should also remember their local fluctuations. Okay? Yes?
What happens when the combustion time and then scale are larger than the Kolmogorov scales? If we plot the reaction, if some reactions are slow?
Well, I mean, this is another good point. We should always keep in mind. Here we said we compare, the Karlovitz numbers compares. Yes. So the question was, what happens if a reaction is slow and it has a different interaction with the turbulence? What we said here was the Karlovitz number. It compares the Kolmogorov timescale with the chemical timescale. Now, what is the chemical timescale? If we have 1,000 reactions, each single reaction has a different timescale. Okay, so very good point. We should keep that in mind. The chemical timescale that we use here is one that tells us something about the flame propagation. But if we talk about pollutant formation, for example, pollutant formation lives on a totally different timescale. So for that, then, I would have to form a new Karlovitz number. I have to compute a Karlovitz number that doesn't use as a timescale here was SL, or was LF divided by SL. That was our timescale here. I need to use a different timescale. I need to compute my Karlovitz number, and then I can still see, where things are. But that's a good point. We should keep these things in mind.
Also, can you still use the gradient transport analogy in that case?
The question was, can you still use the gradient transport analogy in that case? Here, we don't use a gradient transport analogy, right? We have here we just use this Levitzet function. If you solve species transport equations, then, as I said earlier, you always need to be mindful of these. You need to be mindful of these, sharp gradients in LES at least. In RANS, you don't. And then, secondly, you need to think of can you still use these simple assumptions? Actually, it turns out if the chemistry is very slow, then you can still do that. If the chemistry is very fast, then it's not a good assumption. That's what we also saw here in our example. So if the chemistry is slow, is a better assumption than if the chemistry is fast. Okay? Okay, so then we'll talk about non-premix combustion in non-previous combustion, we said, so switching gears, non-previous combustion, we said earlier that that we want to use conserved scalar-based methods. And the conserved scalar-based methods, we use this mixture fraction as a conserved scalar. The mixture fraction tells us locally if the composition is lean or rich, or stoichiometric or whatever. And then, it just turns out that's a very important parameter already that's a very important parameter already to describe the non-previous combustion process. So the mixture fraction again is defined. We define it like this. This is again, nothing else than what we did before. You see here. Again, this comes from our German slides. I mentioned this lambda here is the air-fuel ratio that people in Germany like to use. Just take every time you have a lambda here, take 1 over equivalence ratio, because it's nothing else than 1 over the equivalence ratio. So, but this is nothing else than repeating what we said earlier. This is how we can define the mixture fraction. Then again, here the mixture fraction. It's for stoichiometric conditions. It just depends on the fuel and the airstream, and you can compute this stoichiometric value. Once you know the stoichiometric value, you can also then locally determine what the equivalence ratio is. So there's a direct correspondence between equivalence ratio and the stoichiometric, between the local equivalence ratio and the mixture fraction. And again, mixture fraction 0 means pure air, would also be equivalence ratio of 0. Mixture fraction equal to 1, that would be equivalence ratio of infinity. And mixture fraction is stoichiometric, that would mean equivalence ratio is equal to 1. Okay, so that's mixture fraction. There's a simple transport equation here. That transport equation is has no source term. That's the beauty of it. It could have a source term, but not a chemical source term. For example, if you look at liquid fuels, so you inject the liquid fuel. Here we typically use this mixture fraction just to measure the gas phase species, and so the evaporation then of the droplets, that would add a source term here in this equation, and so. That would be a source term from evaporation, but there's no chemical source term here. So once we have this, let's say you can solve this somehow, and you know all the statistics in the flow field. You know all the statistics of the mixture fraction. You know the mean and the full PDF. If you know the PDF of mixture fraction, and now let's just say, for the sake of argument, let's just say the temperature was a function only of mixture fraction, and that is the case, let's say, for infinitely fast chemistry. Then it's very simple. I can just do this convolution here, and then I get the mean. And again, I could get all other moments. I could get the variance, I get the skewness and whatnot. I can get all moments here of this thing. So. Now, if the temperature is a function not only of mixture fraction, but also of a few other parameters, then I would need for the same thing, I would need the PDF or the joint PDF, not only of mixture fraction, but of all these parameters. Okay? So let's see what. So if we want to use this is what we want to use. If we want to use this, then we need to know these two functions. First, temperature is function of some parameters, and then secondly, the joint PDF of these parameters. Okay, that's the idea, and we can try to see how we get this. So let's start out with the PDF. Here, only of the mixture fraction. Let's say we derive an equation for the. I was confused about the time. What time should we break? At 11, right? At 11. Oh, and today we should have 15-minute breaks, right? Because that's why I was too early in the last break. Okay, so we give you 15 and a half minutes then in the next break. Actually, I said this before. I mean, there's always so many questions in the breaks that I think is very good to have 15-minute breaks. It was just that other things are important also in life. So coming back to this. So let's say we have this equation here for the mean, and we also have an equation for the variance. That's an equation also we derived, I think, earlier. Let's look at it again. The variance here of the mixture fraction, this variance equation is a time-dependent term, convection term. You see here turbulent transport. Yes, turbulent transport has no source term, so we can just use gradient transport model. So this term is closed. Here we have, this is also a scalar flux. See, this is the scalar flux of the variance. This is the scalar flux of the mixture fraction itself. So we can also use here a gradient transport model to close this, and then here we have the dissipation rate. And last time we said the dissipation rate, we compute this by assuming that the time scale for the large scale time scale for the scalar is the same as the large scale time scale for the velocity field. The time scale for the velocity field is epsilon over k. The time scale, it is actually k over epsilon. The time scale for the scalar field is the variance divided by the dissipation rate. So from that we can compute the dissipation rate like this. And there's a factor here. This is what we call the time scale ratio. And this factor, that is a lot. That again, has many different values. People use a factor of 2 typically, sometimes a factor of 3. If you evaluate it from DNS, you see sometimes it goes up to 10 or maybe 100 or whatever. What does that mean? It just means it's not a good model. Okay, it just means it's a model, but it's not let's say it's not a perfect model. Anytime you rely on these constant coefficients, is usually not so good. So that's why in LES you can very often formulate these dynamic models, and so that's much better because the dynamic models, they compute these coefficients given the information LES has about the local flow. In LES, it's very hard also to build dynamic models for something like a dissipation rate. You see this all the time, but very often it's not right. Why? Because look back at the energy spectrum. We had the energy spectrum, E of kappa. Kappa here is the wave number. It kind of looked like this. And so we said, this here, that's the inertial subrange. And then this here is these are the large scales, and these are small scales. And we said all the dissipation happens right here. Because this part here, inertial force are so large that viscosity is not important. So all the dissipation happens right here. So we said then also, when we do LES, we basically cut off this thing with a filter. We filter all the high wave number content out, and we just solve this. But then we use these dynamic models because we have a lot of information about the dynamics of the flow here. And then we can use this to estimate what happens here at these smaller scales. Okay? Well, that's okay. But now this is the spectrum of the energy. Okay? If you plot the spectrum of the dissipation, then it looks like this. So this here would be the dissipation spectrum. Okay, so I put the same kind of scales here. So one thing you see is that the dissipation happens all at the small scales. Okay, so now think again in terms of dynamic models. You have to evaluate the information on the large scales and try to estimate then what happens at small scales. There's no information on large scales because this happens all at the small scales. There's no dynamic model really, no direct, let's say, dynamic model for the dissipation rate. You can be smarter than just doing this and come up with ways to still develop dynamic models, which is good. But this brute force approach by just saying, I evaluated the information here and use it to estimate what happens here, that for the dissipation rate doesn't work. And by the way, because this is the dissipation spectrum, this is a dissipation spectrum. The chemical source term, it also looks like this, right? Chemical source term, chemistry only happens when you have molecular mixing. Molecular mixing, happens on these small scales. So also the chemistry happens on these small scales. So for the chemical source term, it's the same thing. No dynamic model. People don't do that though. I mean, there's maybe 1 or 2 papers 20 years ago where people tried to do this, but that's something important to keep in mind. So this thing here, dissipation rate, is incredibly hard to model. Okay, and that's and it's very important. Okay. Good. So now let's say we solve these equations. Then we have the mean and we have the variance. So these are the first 2 moments of the distribution. And then typically what we do is we presume a functional form for the distribution. So you could say, for example, it's a Gaussian. Okay? Gaussian is actually not so bad. Why is a Gaussian not so bad? Because of the central limit theorem. Central limit theorem says if you have a random variable that is basically it's composed of many different independent random processes, then you get a Gaussian. That's what it is. So in life, many random processes that you look at, they are Gaussian. You know this, I can't remember what this experiment's called. You know this nail board where you have you have a box, and the front side is glass, and you have a lot of nails in this thing. They're distributed in some pattern, and then you put a marble inside from the top, and it goes through the nails. It falls down, and you do 150,000 marbles, and you get exactly a Gaussian distribution. Right? They have this thing in San Francisco in the Exploratorium. If you ever get there, you throw your marbles and you make a Gaussian distribution. So why is that? Because the marble, if you just drop it on one pin, then it goes left or right, and that doesn't give you a Gaussian because that's only one random process. But every time this thing hits a new nail, it's a random process. It could go left or right. And so you have many of these, then you get a Gaussian distribution. Okay? So in turbulence, it's the same thing. You have a parcel of fluid, and you have an eddy that brings it here. The next eddy pushes it over here. Yet another eddy does this. And so there are many different eddies or independent eddies that do something. So you would expect to get a Gaussian distribution. So Gaussian is not bad, but what's the problem with the Gaussian for mixture fraction?
Opposite.
Pardon?
Kind of opposite. We have 0 at the...
No, it's not opposite. There is a problem, though. It's not bounded. Gaussian gives you it's never 0. So if every value has a probability density, and so of course the mixture fraction is bounded between 0 and 1. So what is a Gaussian written for a bounded variable? Something that is not a Gaussian written for a bounded variable, but a Gaussian that can be applied, or something that looks like a Gaussian but can be applied to a bounded variable is the beta function. So what the beta function is shown here for different values of the parameters. What the beta function does is this: if the variance gets very large, takes its maximum value, then you get a double delta function. Delta function at 0, delta function at 1. That makes perfect sense for us because if you go very close to the nozzle, did I have a nozzle here? I do a measurement very close to the nozzle, I'm very likely to get either z equal to 1 in the fuel or z equal to 0 in the air, but nothing in between. So that would be my, if it's perfectly unmixed, that would give me a double delta function. And then when it mixes more and more, and the variance, let's say, becomes very, very small, the variance becomes very small, and the distribution is away from the boundaries, then this delta, the beta function, it actually goes to a Gaussian. Okay? So if you're away from the boundaries, it will give you a Gaussian. When you approach the boundaries, then you get these delta functions.
Is this formulation for temperature only valid for adiabatic then? Because I see that when the combustion is done, you have the same temperature.
The question is this formulation valid for only adiabatic cases? Well, maybe I see what you're saying. So, but let me say, first of all, here for now we're just talking about the conserved scalar, right? Now here you're saying, this here, does this have to be adiabatic? Well, we haven't said anything about this yet. The only thing we said, if T is a unique function of mixture fraction, and we know the PDF of mixture fraction, then this is the mean. There's no arguing about this. And by the way, this doesn't need to be temperature. It could be any function. Any function of mixture fraction, there's no arguing about this. So let's move on, and then maybe you can ask question again if it comes up again. Okay, so this is how this looks like, the beta function. It has these alpha beta parameters here, and it has this gamma function. Gamma function, if you want to evaluate this, it's a function that you have a library, is in the libraries on your computer. And alpha beta, here you see they depend on the mean and on the variance. And the variance here is the maximum possible variance, maximum possible, that is always equal to z times 1 minus z. That's easy to show because that will give you, so depending on the value of z, that's different if the maximum possible value, if z is 0.5, this would be 0.25. But if this here gets very small, for example, if the mean gets very small, then also the maximum possible variance gets smaller. But anyways, the maximum possible variance this here always gives you the double delta function. So you see if this here is maximum, then it's equal to this. So this here would be 1, and then, this would be, this is 1, minus 1 is 0. So in that case, it's 0. So when gamma is 0, it gives you a double delta function. So gamma gets small, it goes more towards this double delta function. So you see here, this would be something with a smaller variance, larger variances. You get this double delta function, or you can also have this delta function on one side. Okay, so this is not a perfect model, but a lot of people actually took DNS and experiments and all of this and evaluated this, and actually it's pretty good. You apply the same thing to reactive scalars. You think it's good or not? There's also central limit theorem would also apply to you could imagine, applies to temperature. He says not good. Usually it's not good because there's no reason why it should be good. You can imagine that, for example, infinitely fast chemistry, what's the probability of finding a fuel, let's say at stoichiometric conditions? It's 0. Why? Because the fuel, the chemistry always takes it away. Okay, it's just like you put your marbles in this box, and let's say there was one compartment that has a hole. That's the chemistry. Okay, then you will never have a ball in that hole. The PDF always goes to 0 at that point. So the PDF itself, a presumed PDF works quite well for non-reactive scalar. Presumed PDF, it doesn't really work for reactive scalars. Okay, good. So that's the PDF part. Then the second part was this function. And this function now, in these conserved scalar-based methods, so these conserved scalar-based methods, they basically all use this beta function for the mixture fraction. But then the question is, what do you do with the second part would be this function here, t of z, or t of some other parameters here. And so these are the different combustion models. We already talked about these two in the limit of infinitely fast, irreversible chemistry. You have, or infinity chemistry in general, the temperature and the mass fractions are only a function of mixture fraction. Okay? Now, this always given a certain energy level and given a certain pressure. And so this means that for infinitely fast irreversible chemistry is the Birk-Schumann solution we talked about. So, you can just plug this in here. Now we have a presumed PDF for this. This here is just the Birk-Schumann solution. So you can get the temperature, mass fraction, density, everything with very, very simple functions. Then there is infinitely fast reversible chemistry. That's chemical equilibrium. And then, for that also, the solution is only a function of mixture fraction. And you can evaluate these things very easily. Okay? So these are two models, but keep in mind, equilibrium for hydrocarbon chemistry on the rich side is very bad. Shouldn't be used. It's very wrong. On the lean side, it's not so bad, actually. For hydrogen, it's good also for rich conditions. Okay, and then the other thing here is, so the other, let's say, two models are the conditional moment closure model, where the solution now, where you solve equations similar to the Fleming equations. Actually, in the first order, which is what everyone uses, is basically exactly the same. Well, I mean, the idea is the same, or the equations are roughly the same, let's say. And the second one here is the Fleming model for non-premixed combustion. And here we assume the chemistry is fast, but not infinitely fast. It's just fast enough that these assumptions hold to good approximation. And then the solution, as we saw earlier, when we look at the Fleming equations, they are a function of mixture fraction and also the dissipation rate. Okay? So we'll talk about this here for 1 minute, and then we want to talk about this here in a little more detail. Okay, so, well, this basically, I said this already. This was the Birk-Schumann solution. This gives you temperature and mass fraction as function of mixture fraction. You can just plug this in here, beta function. And this, so the only thing you do in a code, let's say you want to code this up, it's very simple. You just have the mixture fraction, mean mixture fraction equation, mixture fraction variance equation. And if now in one cell you have the mean and the variance of mixture fraction, you can, from this, you get the beta function, and then so you know this, and then the beta function, and then you use this here to get the mean temperature. Now, let's say you would want to do this. The way you would do it is like this. You would say, the way you could do it is this. You have these functions, this. You store them in your code somehow, or is an equation, so you can compute them easily with a few parameters like q and so on. And then you always compute, you have z mean and variance, and you can compute using this gamma function and so on. You compute the beta function, and then you do this convolution, or you evaluate this integral here, and then you have the mean temperature. That is one way to do it, but that's not how most people would do it. Why? Because this evaluation of these gamma functions and the beta function, that's actually quite expensive. So if you look back at what is this beta function, the beta function, this is a function, and it depends on two parameters, the mean and the variance. Okay? So let's say you evaluate this. So in this case here, in this specific case, you know what the solution is. Okay? So you can take a value of z, mean, and one value of z variance, and then you know what this is, you can evaluate the integral, and you get one temperature. Okay? So each combination of z mean and z variance gives you just one temperature. So it's easy then to say, before you actually start a calculation, to evaluate this integral for any possible combination of z mean and z variance. Okay? Let's say you say, I want this to do this for 100 different values between for mean mixture fraction between 0 and 1. So 0, 0.01, 0.02, and so on, and 100 different values for z variance. Then you have a fairly good discretization of the space, and you just get 10,000 values. Okay? You put these in a table, and maybe 10,000 here. Let's say here you have a few species, whatever. You get let's say here for fuel, another 10,000 values, and so on. So, but it's a fairly small amount of data. And then what you do in your actual code, you solve this mean and the variance equation. And then once you come to in each cell, then you have these two values. You just go in your table, you interpolate in your table, and you have the temperature. Okay? So you never need, in the actual simulation, you never actually need to evaluate the beta function. You just do this beforehand, once and for all. Okay? So that's kind of the idea, of evaluating these. This is the solution. We just mentioned this. So, good. So, for the flame, I mentioned, so these are the infinitely fast chemistry models. You would do the same thing, by the way, with the equilibrium, because you also know these functions. You can pre-integrate this for given values of z mean and z variance, tabulate this all, and then just use the table in an actual simulation. So now we want to talk about this flamelet model. And maybe quickly here, we talked about the basic idea was that we have a scale separation here between the flame scales again and the turbulent scales. I said this a few times. We don't assume infinitely fast chemistry. We assume the chemistry is relatively fast, but not infinitely fast. And the only thing we really do assume is that the inner reaction zone is thin compared to the small scales of the turbulence, and then the inner layer here has still a laminar structure. And so that's the idea. Then again, here this is just a repetition of what we did last time. We take the governing equations here for temperature, mass fraction, and mixture fraction, and then we do this transformation. We take the physical coordinates. We say locally we start out saying the x1 is normal to the iso to an iso mixture fraction surface, and then the other two, they go in the direction of this surface. And then we do a transformation here from x to this z, mixture fraction, and z2, z3, and tau, and these are the same. But as we said last time, you need to give them different names to make sure you're talking about different coordinate systems. And then these are the transformation rules. This is all written in a little more detail than what we did last time. You see here all these individual terms. And you see some of these terms they drop out, and some of these terms they still remain. And then these are the final transformation rules. We plug these in, and then this is the equation we get. Again, there are these terms that here in z2, z3 direction, and then we say, okay, if the changes in direction of z are larger than changes in direction, or let's say, if you sit on the surface of stoichiometric mixture, and you look at changes in the direction of the gradient of z, so that's where the equivalence ratio changes. If these changes are much larger than changes along the flame surface, then we can drop these blue terms here, and then only the red terms remain. And again, that actually is, that's very often a very good assumption. Especially when we have no extinction, then it's usually a good assumption. Right. Let's look at these terms here again. This is what's remaining here is an unsteady term. And then we have this term here where we said this is the scalar dissipation rate, so this is kind of a mixing term. And then we have the chemical source term. And so these are the only remaining terms. This is a 1D set of equations, unsteady set of equations. This also is a DNS, and we had looked at this here before. The blue line here is stoichiometric condition, and you see how actually it's interesting now to look at the assumption we made. Maybe I can stop this at some point. The assumption was, let me see if I can stop this. The assumption was that the changes, if I go normal to the blue line, they are much stronger than changes if I go along the blue line. And you see here for most here, for example, for most of these cases, that is actually a very good assumption. Sometimes here, in particular, this DNS was done to look at local extinction phenomena. And if I have local extinction like here, then it's not a good assumption. Then you see here also, right in this point, the change along the flame surface also is very strong because of extinction here. But otherwise, is not. There was a question last time, shouldn't this break down when the dissipation rate gets very large, because then the chemistry is slow? But you see the opposite kind of is the case, because you see this here is very high dissipation rate, so that's why the flame is very thin, and this here is kind of low dissipation rate. This is why the flame here is thicker. And you see that here, this assumption that changes in normal to the blue line are much larger than along the blue line. Here, it's even better satisfied than in these regions. So the higher the dissipation rate is, the better the assumption actually is, up to the point where you get local extinction, and then the assumption can break down. Okay? Okay, so this is, I'm trying to always remember the break. So let's stop here and then see how we apply this then in turbulent combustion after the break.